Hey everyone, in the last video we have seen that how maps reduces the time complexity so much by just taking some extra space. In this video we'll be looking to the internal structure of another map and how to use it. In fact, in the last video also we have used another map and seen how it reduced the time complexity so much. The basic difference between an order map and another map is only the internal structure and the time it takes. So the syntax of order map and another map remains the same, just it differs in the internal structure and the time complexities. So let's dive deeper in the internal structure of an order map. So the basic definition remains the same as of maps. The only thing changed here is the syntax and the internal structure basically. So consider this all as a long series of array that is declared internally by the system itself. So basically on our map itself to a array rather than using an internal self-balancing binary search tree that map uses. So for understanding it better, let us consider an example that we used in our last video also. So what is this out here first of all? So it is a long array declared by the system itself for storing an another map. So how does it work first? Let us consider we are going to insert a name in our map. So basically this is a roll number and this is a name. So we are mapping John to 5. So what another map does is it takes this map actually, that is a pair, to a hashing function, and this hashing function gives the index to store the name John in our this long array. This array is declared by the system internally and we have no control over it. So this hashing function will be taking this 5 suppose and doing an operation something like this. So this number is 5 is modulo with size. Let us consider the size of this long array declared by the system is 1000. So we'll be doing 5 modulo 1000. So it will give us 5. Basically this will be a very large number declared by the system, but we are just for the simplicity we are considering this as 5. So we got our index and we'll take this name John and insert to the index 5. So it will act similarly for other elements as well. So if I insert some other element like Mark, it will go to this hashing function, then calculates its index and insert this into this array. Again for Diego it's happens same for Marco and other names as well. So basically it will be a long array and it will consist of various names calculated by this hashing function. So you may ask now how it works better than the map. So here's a small trick. Suppose you want to access this element zone. So you access m of 5. So again it will go to this hashing function and this all operation happens in a constant time. So you'll get 5 and you directly access the array as 5. You don't need to traverse the whole array. You just do a of 5 suppose a of 5 and you will get this John name directly. So you don't need to traverse this array as we have done in the binary search tree in the previous video. We traverse from the top then go to the certain element we want. So there it was taking a log n of time, that was height, and here you can directly access it in a constant time. So there is a problem with another map as well. So basically if you insert one more student with roll number 5, this doesn't happen actually, but just let's say suppose there is a situation where for one index there could be a more names. So what happens there? You insert John, you go to this hashing function and insert John out here. Suppose another name a person X come in and then you do m of 5 equal to X. It again goes to this hashing function and generate the same index and you find that John is already present in there. So again you need to find another index. How that is done? That is known as probing. Basically it is a hashing concept. There are various concepts: linear probing, quadratic probing, double hashing and many more to like avoid these collisions. This is also known as collision. We'll be finding some another index, then we'll be storing out there. So here's a lag in the another map. If there is a collision, it again takes big O of n, that is greater than the search time of a binary search tree that is used in maps. So it take more time than the maps as well if there is a collision. Otherwise it can happen in just constant time, and you can access this element in a constant time, so it's very fast, but there shouldn't be any collision. So let's start with the code. The first thing we need to do is to include the Unordered map header file. So it's Unordered map, and for ordered map it's just map. So basically we'll be declaring a order map, something like this. This is roll number and this is name. So it just maps a integer to a string. So basically roll number to a name. So let us include first our namespace as, so it will remove this error. Okay, great. So we have successfully declared another map here. So it's basically map an integer, that is roll number, to a string, that is name. So let us look how to insert a value first. So for inserting a value, it's just same as the ordered map, m of 40 equal to Rohan. So roll number 40 is mapped to a name. So how does do access this element? We just do m of 40. Great. Let's compile it and check. Map cpp. Great. As you can see, 40 is returning this name. So basically similarly we can also insert more names as well. Great. So let us use an iterator. So for it you have to declare an iterator of the same type. So integer string, then again you have to give this scope resolution operator and iterator equal to it. So basically it equal to m dot begin we need to do first, because it will give to the base address of the map. So for that we'll have this thing and it. So this will give the n address till the it doesn't reach the n address of the map. It will keep on iterating, and it plus plus. So basically it plus plus travels to the next address where the element is stored. So basically this it returns a pair. So a pair can be accessed through a arrow keyword, and there are two keywords, first and second, that will give access to the key and value respectively. So basically like for this element, suppose this is first and this is second. Let us compile and check. As you can see, it is first and it is second, key and value. So we'll be not going into much details like map, because the overall syntax of another map and map is same. You can have a look to the video of ordered map. So basically the main purpose was to differentiate between the internal structure of map and another map. So there is one more difference between map and another map, is in map the elements are arranged according to the value of key. So it is sorted according to the values of key, but in another map it is not. So let us check by modifying our code a bit. So it's map m of, let us insert a value 25 and name it something quality. Okay, let us check display and check. So you can see it's 25, 40 and 41. Okay, let us insert one more element. $100. Great. Let's compile and check. As you can see, it is arranged as you are inserting it. So if you insert one more element, it is come in the front of this map again, but it is not the case with the ordered map. So let us like convert this map to another map, as everything is same in case of map as well, that is the syntax and all, so it won't be affecting us much. Let us look. As you can see, in case of map, it is arranged based on the value of keys actually. So first 25, 40, 41, 100. Even the 100 was inserted at the last. So basically it is a sorted way. So you need to differentiate between when to use ordered map and when to use another map based on the situation of the problem. So just keep in mind that maps insert the element and keep it in the sorted order according to the values of key, whereas the another map keeps in it in the order it was inserted. If you want to see these code samples, I'll posting down the link of this code sample to my GitHub page where I have included all the code samples for these containers, so you can have a look.